This video is Module 3, Protocols and Models for the Cisco Netacad Introduction to Networks course 702. In this course, we're going to look at the module objectives of rules, protocols, protocol suites, organizations or the standards organizations that set the protocols and set all the rules, referencing models, data encapsulation, and data access. So for rules, when we communicate in a network, we have to have a way for two devices to communicate with each other. So very similar to speaking the same language. So if two humans were going to communicate together, they need to speak the same language. So if one person speaks German and one person speaks English, they may not be able to understand each other. So the organizations for computers got together around the world over time and said, we need to have a common way to communicate. And those communication fundamentals are what the guidelines and protocols that we set out, or not we, but the internet community, networking community, has set out to say, here's how these devices are going to communicate with each other. So there's three elements to any communication. You need to have a source, someone that's sending, someone that's receiving, and then how is that information going to be sent across? And that's the media. That's going to provide the path of communications that are going to occur. So for the protocols, all communications are governed by protocols. So we say we have to have a common way to send this information from one person to another or from one device to another. So protocols are the rules that communications follow to make sure that that information flows properly. And the rules are going to vary depending upon the protocol. So the message, you have the source, you have the transmitter, the medium, the receiver, and then the message destination. And then over here, you have the same thing. You have your message source, the transmitter, the medium, the receiver, and the destination. When we establish the rules, individuals use established rules or agreements to govern conversation. And as I used the previous example, we say we're going to speak in English or we're going to speak in Spanish. In this case, we're going to speak in network language or networking language. So the first message is difficult to read because it's not formatted properly. And so if you just, wrote a message like this, you may not be able to understand it if it's not written in proper English. The words are English, but they're not in a proper order. So in the second one, rules govern communication between humans. It's very difficult to understand messages that are not correctly formatted. And in the same way, networks cannot communicate if they're not formatted properly. So what we do is we have protocols that account for setting up these rules of communication. So an identifier, so there's an identifier for the sender and the receiver. There's a common language and grammar. There's speed and timing. And then there's confirmation or acknowledgement requirements. Common computer protocols must be in agreement and include the following. You need to have encoding. You need to have the proper formatting and encapsulation. We need to set the message size. We need to set the timing and the delivery options. The encoding, it's the process of converting information into another acceptable form of transmission or for transmission. Decoding reverses that process to interpret the information. So the message gets wrapped up or encoded, and then it gets transmitted, it gets to the other end, it gets decoded and read. The message formatting and encapsulation, when we send a message, it needs to use a specific format or structure so that both the sender and the receiver know how to properly send that and then read it and then recover it. So the message format depends on the type of message and the channel that's used. So much like a regular human letter. So if we write who it's going to, the message, and who the sender is, and then we say, here's our sender address, here's our recipient address, and here's our permission to send it across the network. The same thing happens with message formatting and encapsulation. We have our message here that's broken down. We have our source, we have our destination, we have our length, we have our version that it's being sent on. This is byte 1, byte 2, byte 3, byte 4, and then it's 40 bytes total in this package. Encoding for message size. So when we send between two hosts, we have to have an appropriate format for that medium. So messages sent across the network are converted into bits, ones and zeros. The bits are encoded into a pattern of either light, sound, or electrical impulses. And the destination host must decode the signals to interpret the message. The timing includes flow control, That manages the rate of data transmission, and it defines how much information can be sent and the speed at which it can be delivered. The response timeout is it manages how long a device waits when it does not hear a reply from the destination. So it sends it, it's got a response timeout. It says, your time's up, you didn't get a response back, and so it's either going to send another packet or it just stops sending. And then we have to have the access method. That determines when someone can send a message. There may be various rules governing issues like collisions, and collisions is when packets start hitting each other and colliding on a network, and that's when more than one device sends traffic at the same time and the messages become corrupt. And some protocols are proactive and attempt to prevent collisions, and then other protocols are reactive and establish a recovery method after the collision occurs. So for our message delivery options, we have unicast. That's one-to-one communication. That means a unicast, you have a source to a destination. You have one-to-one. Multicast means you have one-to-many. You have one source sending out to multiple, in this case, these two right here. And then you have broadcast, and that's one to everybody. Now, when we look at the node icons, documents may use the node icon, typically a circle to represent all the devices. And this figure here shows you the node icon for delivery options. So the orange is the sender, the green is the receiver. So here we have a unicast. Here we have sending it to multicast. And here we have it sending to broadcast to everybody. The next thing we're going to look at is protocols. Protocols are the rules that we set up for networking. They can be implemented in software, hardware, or a combination of both. So the protocol type, we have network communications that enables two or more devices to communicate over one or more networks. Then we have security. That secures data to provide authentication, integrity, and encryption. We have routing, and routing tells us how to or it enables routers to exchange route information, path information, and it selects the best path for that information to travel. And then we have service discovery. That's used for the automatic detection of devices or services as they come online or as they go offline. Devices use agreed upon protocols to communicate. Protocols may have one or more functions. Addressing identifies the sender and receiver. Reliability provides a guaranteed delivery. Flow control ensures data flows at an efficient rate. Sequencing uniquely labels each transmitted segment of data. Error detection determines if data has been corrupted. An application interface is the process-to-process communications between network applications. With protocol interaction, networks require the use of several protocols. Each protocol has its own function and format. In these examples here, the protocol for HTTP, or Hypertext Transfer Protocol, that governs the way a web server and a web client interact, and it defines content and format. That allows us to be able to take a web browser, open up a web server web page, and that web page be able to be formatted and displayed on our screen for us. The HTTP protocol does that for us. The TCP protocol, or Transmission Control Protocol, manages individual conversations, it provides guaranteed delivery, and it manages flow control. The Internet Protocol, or IP, delivers messages globally from the sender to the receiver, and Ethernet delivers messages from one NIC to another NIC on the same Ethernet local area network. When we look at protocol suites, protocols must be able to work with other protocols. So a protocol suite is put together, and it's a group of interrelated protocols that are necessary to perform a communication function. We have sets of rules that work together to help solve some type of problem. And the protocols are viewed in terms of layers. We have higher layers and lower layers. Lower layers are concerned with moving data and providing services to upper layers. Along the physical layer, the rules layer lay out rules for how the content is going to be sent, how fast it's going to be sent, and how much can be sent at each time. Here are some of the protocol suites that we use. TCP/IP, that's the most common protocol. It's maintained by the Internet Engineering Task Force, or IETF. You have the OSI, that's the Open Systems Interconnection Protocols. That's developed by the International Organization for Standardization, or ISO, and the International Telecommunications Union, or the ITU. You have AppleTalk, that's proprietary suite released by Apple, and Novell Network, proprietary suite developed by Novell. I used Novell back in the 90s. Not a lot of people use it anymore. AppleTalk's not used very much anymore. The two most common that you're going to come across and learn in this course are TCP/IP and the OSI. An example of TCP/IP protocols, they operate at the application, transport, and internet layers. So application, transport, internet, and then you have network access, which is the Ethernet. The most common network access layer LAN protocols are Ethernet and WAN, or WLAN, wireless LAN. TCP/IP is the protocol suite used by the internet and includes many protocols. TCP/IP is an open standard protocol suite. It's freely available to the public and can be used by any vendor. A standards-based protocol suite that's endorsed by networking industry and approved by standards organizations and ensures interoperability. I can't get that word right. Interoperability means they work together. And I will just tell you as a side note, you do need to learn these layers. You need to learn the application layer, the transport layer, the internet layer, the network layer. You may not need to know all of the details by memory for this course, but you need to be very familiar with them going through this course and for the exams at the end. So for the communication process, a web server encapsulating and sending a web page to a client is referenced here. We take the Ethernet, the IP, the TCP, and the data. It's all packaged together or encapsulated, and it's sent across the medium. It's sent in ones and zeros. So you see the ones and zeros going across. And on the other end, it gets decapsulated or de-encapsulation, and the web page is then displayed on the browser. For the standards organizations, we have some different standards organizations, the IEEE, you have the Internet Assigned Numbers Authority, the ITU, the TIA. You don't need to memorize all these, but you need to be familiar with them. They are governed by open standards. Those are encouraged so that you can have interoperability, competition, and innovation. Some of the standards organizations they should be vendor neutral. So they shouldn't be, and by vendor neutral, I mean they don't favor one like a Microsoft or a Cisco or an Amazon. They work for all organizations. They are mostly nonprofit, or should be. I think all of these are nonprofit, established to develop and promote the concept of open standards as well. The Internet Society promotes the open development and evolution of the Internet. The Internet Architecture Board is responsible for the management and development of Internet standards. The IETF develops updates and maintains the Internet and TCP/IP technologies. And the IRTF focuses on long-term research related to the Internet and TCP/IP protocols. The IANA and ICANN, or ICANN, I pronounce it ICANN, the Internet Corporation for Assigned Names and Numbers, ICANN, they coordinate the IP address allocation, the management of domain names, and the assignment of other information. And the IANA oversees and manages IP address allocation, domain name management, and protocols. And I'm not going to read down through these, but I'll just the IEEE, the EIA, the TIA, and the ITUT. You need to be familiar with these. Those most likely will be on an exam in this course, so you just want to be familiar with what each one of them does. You probably don't have to memorize them, but you need to be familiar with which one does what. Now, looking at reference models, the benefits of using a layered model is that it's easy to memorize. The OSI model, I always go from the bottom up, and I use the please do not throw sausage pizza away. That's how I remember it, so I use that acronym, please do not throw sausage pizza away. And what I do is when I go into an exam where I need to have this memorized, I write that PDNTSPA and I write it down on a piece of paper so that I can reference it back during the exam so I don't have to try to memorize it or do a memory recovery. And this is how they match up. Here's how the OSI model matches up to the TCP/IP model. The TCP/IP model has 4 layers. You have these layers over here, but this is how they match up. You have the Ethernet, WLAN, SONET, IPv4, the TCP, UDP, and then the HTTP, DNS, DHCP, FTP. That's at the application layer over here. These 3 layers take care of it over here. Your transport layer, your network layer here, your internet layer here, and then over here we have data link and physical, and here we have network access. Now, the benefits of using a layered model, it assists in protocol design because protocols that operate at a specific layer have defined information that they act upon. It fosters competition because products from different vendors can work together. And it prevents technology or capability changes in one layer from affecting other layers above it or below it. And here's another example of the OSI model. You have application, presentation, session, transport, network, data link, and physical. And then the TCP/IP model, you have your application, transport, internet, and network access. Here it is compared again, side by side. The OSI model divides the network access layer and the application layer of the TCP/IP model into multiple layers. The TCP/IP protocol suite does not specify which protocols to use when transmitting over a physical medium, and OSI layers 1 and 2 discuss the necessary procedures to access the media and the physical means to send data over a network. Next, we're going to take a look at data encapsulation. We segment messages, and when I say we, I mean the network segments messages, but it breaks it up into smaller units so that it can be sent across the network. Multiplexing is the process of taking multiple streams of segmented data and interleaving or interweaving, they tie them together. And segmenting messages has two primary benefits. It increases speed, so large amounts of data can be sent over the network without tying up communication links, and it increases efficiency. Only the segments which fail to reach the destination need to be retransmitted, and so not the entire data stream gets resent. Here's a visual representation of sequencing. So sequencing messages is the process of numbering the segments so that the message may be reassembled at the destination. They may not get there in order, by the way. So package 1 and package 3 may get there at the same time, and then 2 show up briefly behind, and then it will know which numbers and how they're ordered, and it'll put them back together. So TCP is responsible for sequencing the individual segments. So encapsulation is the process where protocols add their information to the data as it goes down. So they encapsulate or they build on it as it goes down. So you have your data, then you have your segments and your packet and your frame, and then your bits. The bits are the ones and zeros. So at each stage of the process, a PDU has a different name to reflect its new function. There's no universal naming convention for PDUs in this particular course. The PDUs are named according to the protocols, and PDUs passing down the stack are as follows: your data stream, your segment, your packet, your frame, and then the bits. This is an example of an encapsulated model. It's a top-down process. The level above it does not process, and then the level above does its process, and then passes it down to the next level, and the process is repeated by each layer until it's sent out through the bit stream. And then on the other side, you get the de-encapsulation process. The data is then de-encapsulated on the other end, and it moves up the stack. So it's received as bits, it goes to the frame, then the packet, then the segment, and then the data stream. For data access, we're going to look at the data link and network layers. They use addressing to deliver data from the source to the destination. And the network layer source and destination addresses are responsible for delivering the IP packet from the original source to the final destination. And the data link layer source and the destination address are responsible for delivering the data link frame from one network interface card to another network interface card on the same network. For a layer 3, the IP packet contains 2 IP addresses at the layer 3. So you have the source IP address, the IP address of the sending device, and then the destination IP address, which is the receiving device of the final destination. And these addresses may be on the same link, or they could be remote out and they get routed out, and that's why we use routers. An IP address contains 2 parts, the network portion or a prefix. We're going to call it network portion for IPv4, and it's called prefix for v6. The leftmost part of the address indicates the network group, which the IP address is a member, and each LAN or WAN will have the same network portion. And we're going to learn more about segmentation and network portions versus prefixes versus host versus networks later on in this course. The host portion, or v4, or interface ID for the v6, is the host side or the non-network side. So the network tells you who is all on the same network. The host portion tells you your individual IDs. Devices on the same network. So when devices are on the same network, the source and the destination will have the same number in the network portion of the address. So for here, if this is our network portion of the address, they'll both have 192.168.1. So they're both on the same network. And then you'll have your host IP addressing. When devices are on the same Ethernet network, the data link frame will use the actual MAC address of the destination network card. MAC addresses are physically embedded into the Ethernet NIC and are local addressing. They're used for the local addressing. The source MAC address will be that of the originator, and the destination MAC will be of the receiver. For devices on a remote network, what happens when the actual destination is not on the same LAN? And what happens when the PC1 tries to reach the web server? And then does this impact the network and the data? So if it's not on the same network and it doesn't have a routing address, it's not going to be able to be sent and received because it's got to be routed and there's no routing information. So the role of a network layer address, when the source and destination have a different network portion, that means they're on different networks. So if we have 192.168.1 and the web server is 172.16.1, they're not on the same network and they're going to have to be routed. So when the final destination is remote, layer 3 will provide layer 2 with the local default IP address, also known as the router address or the gateway. Gateway is used. Default gateway or gateway is one of the common terms that you'll hear. That's the router interface IP address that's part of the LAN, and it will be the door or the gateway to all other remote locations. It's where you get your information gets routed. All devices on the LAN must be told about this address or their traffic will be confined to the LAN only. And once the layer 2 on a PC1 forwards to the default gateway, then the router can start the routing process of getting the information to the actual destination. So the data link addressing is local, and it'll have the source and the destination. The MAC address for the first segment is here. I'm not going to read that out. It sends the frame, it sends the destination, and while the L2 local addressing will change from link to hop, the L3 addressing remains the same. And this is what we have here. This is all local, but if we get sent out, it goes to the router, and then it gets sent through the router or the cloud that we've discussed, and then it gets to the other end, and then it uses the MAC addressing on the other end once it gets inside their network. Since data link addressing is local addressing, it will have a source and a destination for each segment or hop of the journey, and the MAC addressing for the first segment is, in this case, PC1 NIC sends the frame, and the destination router receives the frame, and then it converts it to the layer 3. The MAC address for the second hop is the source, first router. It exits the interface, it sends the frame, and the destination receives the frame. And then the MAC addressing for the last segment is source. You get your second router exit interface, it sends the frame, and then the web server NIC receives the frame. And now if you notice that the packet is not modified, but the frame is changed, therefore the layer 3 IP addressing does not change from segment to segment like the L2 MAC addressing does. The L3 addressing, or layer 3, remains the same since it's global and its ultimate destination is still the web server. So what did we learn in this module? We learned about rules, we learned about protocols, we learned about protocol suites, we learned about standards and organizations, we learned about reference models, data encapsulation, data access, and finally, here's some of the terms and commands that we learned in this module. I'm going to leave it up here for a second if you want to pause your screen. And here we have page 2 of the terms and commands. I'll leave this up for a few seconds for you. And thank you for watching this video. Thank you for sharing it. Thank you for liking it. And I hope you have a great class.